Hello there. Welcome to the keynote on Laziness is the Ultimate Sophistication, both in life and programming. My name is Venkat Subramaniam. I'm going to talk about my excitement around functional style of programming, how practical is it to really achieve that, and how languages like Java make it really easy for us. Well, we've been programming in the imperative style. Most of the predominant mainstream languages provide imperative style of programming for a very long time. Well, in the imperative style of programming, we focus on what to do, but unfortunately, mostly on how to do. Let's talk about this with a really small little example, a trivial example, but nevertheless illustrates the point really well. So let's get started with a little example here. Here's a list of names, half of which we cannot see, but I'm curious, is our friend Nemo in the list? How do we solve this problem? Well, the imperative style, it starts with a ceremony right off the bat. So we'll first of all say Boolean found is equal to, in this case, false. We want to then say for, pick one name at a time from the list, of course, and then we're going to examine, given each of the name, we're going to ask if that name is equal to, well, of course, the word Nemo. Well, if it is found, we declare the victory by setting found equal to true, but not so fast. You better remember to break out of this as well. Otherwise, we'll be continuing to process even after we found the result, which is not very good for performance, especially when we have a very large collection. But not quite done yet. We still have to come back and examine the found, and then we have to say output Nemo found and celebrate about it. But of course, sadly, if we couldn't find Nemo, we'll then declare saying, oh, maybe that Nemo was not found right here in this case. So we'll say Nemo not found. Maybe play a sad music. Let's go ahead and run this code and see. Yay, good news, we found Nemo. That's imperative style of programming. Well, I call this accidental complexity because in the imperative style, we focus on what to do, but also on how to do it. We get dragged into the details of how. We had to take every single element. We have to compare the element. We have to set a flag. And don't remember to break out of the loop. Every single piece is your responsibility, our responsibility when it comes to coding in this style of programming. So imperative style of programming is where we get bogged down with the details. That introduces accidental complexity, makes code really hard to change. That's the past. Every single mainstream language did this to us. But it's not our fault as programmers, but we had to really work with tools given to us and what's mostly available and popular as well. But the good news is the future is moving in a different direction. Almost every new mainstream language today is moving towards the functional style of programming. Well, the future is in declarative style and functional style. Let's talk about declarative style first. Going back to this example, this was a lot of ceremony, a lot of noise to find Nemo. Let's get rid of all the noise and ceremony in this code right here. And then we'll just come down to the found right here and change it to, let's say, names.contains, and then of course ask for Nemo. What all that effort we had to put in is gone. We can quickly come here and get the result. That's an example of declarative style of programming. So what is declarative style? So in the declarative style, we can focus on what to do and not on how to do it. So we focus on what to do. That is our main focus. What are we interested in? So focus on what to do, not on how to do it. Well, the declarative style removes all the accidental complexity in the code. We might ask the question, how does contains really do the work? One answer possibly is, it's doing exactly this. We come up with all other kinds of ideas as to how contains works, and different languages may implement contains differently. But I like a better answer, and that is, I don't care. Okay, maybe that's a little rude, but rather than saying I don't care, we can say it's encapsulated. Oh, that sounds so much better. Well, meaning I don't care. Well, true, we can all agree that there are times we absolutely care. But the beauty with the declarative style of programming is we can get to the details when we care about it. We don't care about it, it's not on our face. In the imperative style, we have no choice whatsoever. The details are in front of us whether we like it or not. We have absolutely no escape from the details. So in the declarative style, we focus on what to do, not on how to do it. Well, that's declarative. So think declaratively first. Functional comes next. In functional style of programming, we are also using declarative style. Functional style of programming is not new. Thank goodness it's not new. It's not a newfangled idea invented last night. It's been around for a very long time. It's been tried, tested, and been practiced quite a bit. It just was not popular in the mainstream languages. But almost all mainstream languages now are providing functional style of programming, which is really phenomenal. So this is a very old idea, but with renewed interest. What are some of the reasons for it? Well, the world we live in has changed quite a bit. The type of applications we develop, the type of data we process and deal with, a lot of these things are different from applications we developed 20, 30 years ago. But what is the charm of functional style of programming? Let's talk about that right here. For that, let's take a slightly different example here than the names. Let's start with a list of numbers, let's say 1 to 10. Given these numbers, I'll say find the total of double of even numbers. Well, great, I want to find the total of double of even numbers. Well, what does the imperative style do? It beats you down from the beginning, isn't it? Result is equal to 0 for integer element coming from the numbers collection. We then say if element mod 2 is equal to 0, then of course we'll say result plus equal to, and then e times 2. And then when we are done with this whole thing, we can display the output of the result right here in the very end. So we can see the result is 60. That's quite a bit of work, again, an imperative style of programming. We're going to switch here to a functional style of programming. Well, what in the world is functional style? Not all declarative code is functional. Remember the contains method. The contains method is declarative but not functional. But all functional code is declarative. So this is declarative plus higher order functions. So what in the world is higher order functions? Well, declarative is where we say what to do and not how to do it. Let's go to the theme real quick and see the example. So we'll start with an output right off the bat. Numbers.stream, where stream is a fancy internal iterator. We'll call a filter given an element mod 2 is equal to 0. So we get only even values from the collection. Then we perform a map to, let's say, double right here. And then in this case, or map to int rather, map to int, and we will go ahead and double the element times 2. And once we, of course, double the value, we'll call the sum of it and get the total of the double of the even values. When we run the code, notice the result is still the same in this code example. It is declarative because we told what to do. Go ahead and perform the sum operation, perform filter, perform mapping or transformation of the data. But it's higher order because we are passing a function to another function. The highlighted code, of course, is a lambda expression. Lambda expressions or lambdas are anonymous functions. We're passing a function to this filter method or filter function. So in higher order functions, we can pass functions around. We can pass a function to a function, create a function within a function, even return a function from a function. Those make it higher order. So this line of code is functional, meaning it is declarative plus higher order. On the other hand, similarly, this one is functional as well, but this one is purely declarative. So this, of course, is focused on telling what to do. We're not passing any functions to these functions. And that's basically the functional style of programming. But what is the charm of a functional style of programming? The charm of functional style of programming is highly expressive code. So the code becomes a lot more easier to work with, easier to write. Let's look at one example of this to see how beautifully the code begins to flow. I was teaching a Java 8 course for a client, and they had been using Java 8 already, and one of the developers said, can you take a look at our code and critique it? Usually I get scared when people ask this question. What if the code is really highly complex and I cannot understand it? I don't want to insult them by saying anything. Well, in this case, the code was written using Java 8 streams. I just started reading the code, and even I, who doesn't have any understanding of their domain, was able to quickly understand what they were doing. That's one of the biggest charms of functional style of programming. Let's start with a create people list right here. And given a list of people, let's say I want to go ahead and store that here into list, let's say person people is equal to create people. But I want to find the names, let's say, get the names all in uppercase, let's say, and then of course of everyone who is younger than 18. Oh, that should be easy, isn't it? Get the names in all in uppercase of everyone younger than 18. Well, we could start again with the list string over here. So we could say string, and we could say juniors, just to call them as juniors, or kids, if you want to call them kids, though 17-year-old may really object to it, but let's call it as kids, is equal to new arrays, and in this case, array list, and we create an empty list. Look at the ceremony again. We're spending time telling how to do things. And then for a person, given a person coming from the people collection, and what are we going to do with every single person? We say if the person.getAge is greater than, well, less than 18, then of course we're going to say kids.add. Well, then of course get the name of the person, get name, and then to uppercase, and then of course add it to the kids collection. When we are done with it, we'll go ahead and output the values for kids. And quickly glancing at this, we see that there is Jack, one of the Jacks, and Jill, who are less than 18. Let's see if the code produces that result, and sure enough, it's Jack and Jill. But if you look at this code, there are a few different problems in this code. It's verbose to begin with. Second, it lacks cohesion. What in the world am I talking about? Well, look at this one line of code. It's doing one too many things. It had to get the name, it had to transform into uppercase, it had to add to the collection. That's a lot of work. And of course, if somebody comes along and says it's a very long list, make it parallel, you're going to find the nearest exit to get out. A lot of work to make this code parallel, of course. But we can save a lot of effort by going functional on this. That's the charm of functional style. So what is the charm in this example? We can now again start once more output, but this time we will start with people collection, and then we'll get the stream again. We'll do a filter given a person. We'll simply say person.getAge is less than 18. But then we'll perform a map. We'll say given a person, give me the person.getName right here. Or as we would do, we'll refactor this to using method references in just a minute. We can then say given a name, we'll say name.to uppercase right here. And then once we get the uppercase, we can say collect, and we will collect it into a nice little list, if you will. So here is toList. And of course, toList comes from the collectors utility method. So we'll say collectors, and right there is the toList coming from the collectors. Let's go ahead and run this code and see what it does. And of course, in this case, given a person, I should spell it properly. Here's a person. And of course, go ahead and run this code and see that's a Jack and Jill. But look at the function composition we see right here. Given a collection of person, we get all the people younger than 18, get their name, convert to uppercase, and put it back into a list. It becomes a one flow through top to bottom. We don't have to go back and forth to understand. There is no need for the breaks and continues and all that thing we do. It becomes a lot easier. Of course, we could take this one and say string : and use a method reference as well. And likewise, we could use a method reference here too. So we can save quite a bit of effort in reading this code and make it really elegant, if you will. So in this case, of course, given a person, we're going to get the person's name, and then we're going to convert it to uppercase and get the result. This function composition is extremely compelling, and so that's one of the biggest benefits we get out of this. But of course, the question is, what's the catch? That's what intelligent programmers always ask, what's the catch? Well, let's talk about the big elephant in the room. I've never walked into a client site where the minute I talk about Java 8 and functional programming, the immediate question is, gosh, but what about performance? Performance is something extremely important. But it turns out not all languages are created equal. Let's just take a detour and take a look at Ruby real quick. Before I get started though on this, I want to emphasize one thing. I love Ruby. I don't want me saying negative things about a language to be taken as a hateful comment. I'm objective. I want to show good things and I want to show not so good things as well. In fact, I will even point that about Java 8 in the end. I love Ruby. I use Ruby extensively. I've got applications I maintain in production using Ruby as well, as much as a lot of other languages. However, from the language point of view, I like to learn from what the strengths and weaknesses of languages are. The strength of Ruby is pure elegance. It's beautiful. No ceremony. So it's a really good language for a certain type of things we do. Kind of like a bicycle versus a rocket, if you want to think about it that way. There are times when a rocket is maybe the right vehicle to use. A lot of times, bicycle is awesome to use, and I want to be able to pick and choose what may make sense. Let's talk about Ruby real quick. So here I'm in the Ruby source code. Let's talk about a little transformation I want to do. Let's do numbers is equal to, and I want to say 1, 2, 3, maybe a few numbers right here, and I want to take these numbers, but what do I want to do? I'm going to say find the find the, let's say, double of all even numbers. So I want to find the double of all even numbers. Well, that shouldn't be really hard to do, is it? Well, if I want to find the double of all even numbers, I'm going to just take every number, find which is even, double it, and then of course, total it. Well, okay, that's not really that hard. But let's change the problem a little bit. What if this collection were to have different values along the way? Say maybe something's along these lines. I'm going to change it to some arbitrary values that I'm going to work with. So in this example, of course, I've got a bunch of different values, but let's say find the double and of the first number greater than, let's say in this case, greater than what? 50. So I want to find the double of the first number greater than 50. So how would I do this? Well, we all like functional style of programming. It's charming, it's beautiful, it's elegant, how easy it is to understand the code. And Ruby has been supporting the functional style of programming as much as imperative style of programming from day one. So in that sense, Ruby has been doing what Java has been recently doing, providing both imperative and functional style of programming. Well, let's give it a try. So numbers.map, just like how we used a map function right here for transforming, we could use a map function. Oh, but wait a minute, we want numbers greater than 50, isn't it? So we could say filter, and given an element over here, so here is an element, this is Ruby syntax, we could say greater than, we'll say E is greater than, and in this case, 50. And we're going to ask if it's greater than 50 for this particular element. So we'll go ahead and write that function, E is greater than 50 given a number n. I want to simply return this value, we'll say return n is greater than 50. How charming, that's great. Then we'll say a map function. In this case, of course, given an element, we will say we want to double the element, so we'll double the element right off the bat. So this requires us to write a double function which takes a number n, and all that it's going to do is return n times 2. That's awesome so far. But remember, I don't want all of the values, I want just the first value. And we will of course print this result when we are done right here. So we'll say puts and ask it to print the result. So let's go ahead and try this. Line number 13 has an error, we'll fix it. So in this case, numbers, in this case, of course, we're going to say find all. We're going to ask for every single value and then double it. Well, find all is equivalent to our filter right here in Ruby. Well, the first number that's greater than 50 is 54. So the times 2 is 108. We can see that. So that's doing the work. But remember in this example, we really wanted the first value that meets the criteria. But how much work did Ruby really do in this particular case? Well, it turns out Ruby was very eager. It did a lot of work. So if you go over here and print, if you will, in this case, we'll say E is greater than, and then we'll print the value that we are asking for. And then we'll go to the double and then ask it to print the result of double. And then, of course, specify what the value is. Notice all the processing we did. We computed, we checked if every single value is greater than 50, all the way from the 1 to the n20. Then we doubled all the values greater than 50, 54, 61, 77, and 88. And finally, we discarded everything and just kept the first value. What a waste of performance. Ruby is great for what it does, but what if I'm dealing with a large amount of data? In some projects I'm working with, we are dealing with literally millions and millions of data. This would not work really well in such situations, isn't it? So what really attracted me to Java 8 is not the fact that it actually has the functional style of programming. In all honesty, I kind of discarded what Java 8 provided to begin with. Because I said, what's the big deal? Other languages have lambdas, Java now has lambdas, why should I care? But I found there is a lot more than lambdas in Java 8, and that's what really drew me towards Java 8. Elegance is very useful. We would not discard that. Beautiful code is great, code that is expressive, code that is easier to communicate with, awesome, that's great. But performance is critical. Give me performance or give me depth is probably a slogan we can all say. So elegance in the absence of performance is not going to scale really well. So what gives? What do we do? Are we doomed with this kind of programming then, where we can have either performance or we can have elegance, but not both? Well, it turns out that's not entirely true. Let's look at other languages to learn from. Let's turn to a truly functional programming language, Haskell. I really love Haskell for what it does. Let's take a look at Haskell really quickly. If you look at Haskell right here, I'm going to write a function called addAb equals a plus b. So in this case, it's going to return the result total of a plus b. But these functions in Haskell are known as pure functions. Now I write an evaluate function where it takes a value and returns a value. And of course, I'm going to write a main function which has a side effect. I put an equal right there. And then I'm going to say print, and the print is going to print evaluate, and it's going to print add 1 and 3. When I run this, of course, it says 4. However, in this example, Haskell had to do all the work. But Haskell, unlike a lot of other languages, applies what is called a normal order, while a lot of other languages, including Java, use what is called applicative order. So what in the world is the difference between those two? Normal order is quite abnormal, as you can see, not a lot of languages do this, is the evaluation of a function is postponed until the value of that evaluation is actually needed. In this example, add is not going to be called until we step into evaluate. So if add is not needed at all, it would never get executed. Let's prove this. In this case, I'm going to show that add is going to be actually called. Well, I can't put a print statement in there because prints are side effects. So what am I going to do here? Well, the way I'm going to work through this is to bring up the GHCI, the compiler, and I'm going to load up the Haskell file into it. I'm going to put a breakpoint on line number 1, character 16, and I'm going to ask main to be evaluated. Notice it stopped on line number 1. When I say continue now, you can see it produced the result of 4. So I just proved that it executed the add function. Ignore that, we'll come back to it. Now let's go back to this code and simply return a 42. Now when I run the code, it produced 42. But aha, Haskell is smart, a normal order. It says I don't have to evaluate add after all because you're never using the result of add. That's only possible when functions are pure. I'll talk about that in a minute. So because of that, add is never evaluated in this example. Let's prove it. So let's go back here and run the Haskell GHCI REPL again. Let's go ahead and say, in this case, put a breakpoint on line number 1, character 16, but call main this time, and notice it never stepped into the function add. That's because Haskell says there is no reason to evaluate that method add, a function add, because you're never using the result of it. That's efficiency, isn't it? Efficiency is avoiding work that shouldn't be done in the first place. You don't want to be fast, you want to be efficient. When you're efficient, you're automatically going to have better performance because you're not doing unnecessary work. So how is this even possible? How could Haskell do this? That's because we have what are called pure functions. So what are really pure functions? Pure functions give exactly the same result as long as the input is exactly the same every single time. Pure functions will never give us a different result for the given set of input. Pure functions don't have any side effects. So when you run the function, you wouldn't know if they ran or not. Anyway matter, you wouldn't know what their effect was because they have no side effects. So they take an input, they give an output. If you don't use the output, it doesn't matter. It's as if they were never actually run. So what are benefits of pure functions? The first benefit is they're idempotent. You can call them any number of times. For example, you call your bank and say, what's my balance? And then immediately, what's your balance? Assuming you didn't really deposit any money or withdraw, the balance will be the same. In this particular case, usually that's not an idempotent operation because the money in the bank keeps changing. In a lot of cases, it keeps decreasing frustratingly. But the point really is it keeps changing. So idempotency is when you can do the same work repeatedly and gives the same result, like the add function. Referentially transparent. You can call a function and you can replace the function or expression with its value. So for example, in this particular case, Haskell could have decided to replace this add 1, 3 with the value of 4 if it wanted to. It could do this, and that's referential transparency. In fact, Java compiler does that when it knows that the functions are evaluations, expressions are pure. It's easy to memorize the result. Memorization is storing them. So you can put them into a cache and say, the next time you call this function, I won't evaluate it. I'll just give you this result back. This is used in what are called as dynamic programming problems, an algorithmic approach where we use excessive amount of recursion, but we save on performance by memorizing. Code is easier to test. As long as the input is the same, the output is the same, don't have any external dependencies, awesome, that's the dreamland for really having ability to test it very easily. And finally, of course, it's easier to parallelize the code as well. You can throw concurrency into a pure function because it has no side effects. It's not going to run into any race conditions and mess with some shared global mutable state. And it's not going to be affected by state outside as well. But for our purpose, the most interesting part here is it can be lazy. So it can take it easy and wait until it doesn't have to execute it or until the last responsible moment. Laziness is the real charm in this case. And what you just saw here was Haskell being lazy about implementing the add functions evaluation, so it postponed it long enough that it didn't have to do it at all. Other languages that use applicative order eagerly evaluate those things. But like I said, not all languages are created equal. Haskell falls on what I call as safe defaults. It assumes all the functions are pure unless otherwise stated. Languages like Java, Scala, and so on rely on, fearing that functions are mutable unless otherwise stated. So let's talk about Scala just for a little bit. Let's go to Scala real quick. I'm going to create a function right here called compute. This takes a value int and it's going to return, let's say, n times 2. Well, I'm going to go ahead and say val x equal to 4. If x is greater than 5 and compute of 4, let's say, is greater than 10, I want to go ahead and output println, let's say, result 1. Otherwise, I'm going to print out, let's say, result 2. When I run this code, the question really to ask is Scala going to run the compute method? We all know the answer for it. Compute will not run. Why so? That's called short-circuiting. Hey, great! Short-circuiting is another example of laziness. It doesn't evaluate compute unless this one turned out to be true after all. So we know that conditionals have short-circuiting and laziness in place. So if I go back here and say called right here, you will notice that it was actually never called. That's awesome. But what if we take this out of here and call it temp, and we say over here val temp is equal to compute? Sadly though, this time, however, when you run this, Scala called the compute method. Should it have called? No, of course not. We're not using the result of compute, but Scala evaluated compute eagerly. Why did it really do it? The reason is Scala is worried that compute may have a side effect. But wait a minute. It had a side effect a minute ago when we called it with compute right here. So why did it not call it here, but why does it call it now? The answer is very simple. Language spec. The language specifications rule. Language specifications say, even if a function were to have a side effect, we may not call them if those are in a short circuit situation. So language spec. Language says that here are times we will call methods if they have side effect. Here are times when we may not even call it, even if it has side effect. So it really boils down to language specifications. And Scala chose to call methods unless you are using in a short circuit situation, or you predominantly tell Scala it's okay by marking it as lazy. By saying lazy, you are saying don't bother running this if you really don't need it. As you can see in this example, if I change it to a 1, you will notice that it did call it. But if I put a 5 here, it doesn't call it. That's being lazy, as we can see. Really beautiful, isn't it? So you have these tweaks in languages which you can use to control whether the language is going to exercise something or it's not going to exercise something. Very powerful, as you can see. But what's really special about Java though? Well, Java has been predominantly an imperative style and object-oriented style of programming language. So this has been our experience in the past. So when it comes to Java 7 and earlier, we did imperative plus object-oriented. And that's been the real mode of programming in Java itself. But starting with Java 8, what we can do is, sure, you can program, and later, let's say, sure, you can program in imperative style if you want to, but you can also do functional plus object-oriented with the hope that we will do predominantly functional rather than imperative rather. So the real culprit here is not object-oriented. The real culprit here is imperative style of programming. By replacing the imperative with functional, we could still use imperative if we wanted to, but we have the ability to replace the parts, we can get some really good benefits. And the benefit, as you can see in this case, is that charming feature of how we could do this in the function composition style. But before we talk about this though, let's talk about one benefit and how we can achieve that benefit. So the real charm here in Java 8 is that Java 8 actually does something a lot more than providing just a functional style of programming. Java 8 did not walk away saying, here are lambdas, good luck. When I was writing the Java 8 book, I wrote something in the book which really surprised me that even I wrote it, but my statement was that lambdas are the gateway drug, but streams are the real addiction. So the point really is that the lambdas really draw you in, but the streams are the ones that are going to keep you in, because if you don't have performance, you're going to leave as soon as you come in. But how do streams give us performance? Let's talk about that real quick. Let's get back to this example real fast and understand one key difference. Notice that in this example, we have stream. A stream is very different from a list. Let's talk about these two for a minute. Put the word list down for a second, and also put the word stream. List is concrete. On the other hand, stream is an abstraction. What does that really mean? List is a container. Well, this is a series of functions. That still doesn't ring the bell. Think of the word bucket. I can have a bucket with a pile of water. The bucket contains water in it. I can store the water in a bucket. I can come back and use the water stored in the bucket. A list is a container. We store stuff into it. A stream, on the other hand, is a pipe. Liquid flows through it. Data flows through this pipe. It's not for storing things. It's for transforming and moving things. A list is a container like a bucket. A stream is a series of pipeline of functions to transform the data along the way. So in that regard, what does it really mean to us? What it means to us is a stream is a series of transformations. To understand this a little bit better, let's go back to another example we saw earlier. And then we will relate back to this real quick. Let's bring back our sample.rb code right here and take a look at the Ruby code one more time. If you look at this example, watch carefully the execution path this code took. It executed the is greater than function on every single value. So what did Ruby do? Apply the first function on the entire collection. Then it said apply the second function on the result collection. So in other words, that's eager evaluation. Keep that in mind. We'll see how Java does things very differently. In the case of Java, Java is assuming that the lambda expressions are pure. This is one big difference between Haskell and Java. Haskell is a bit boring in my opinion. Haskell will come back and beat you down and say, you will not mutate, you will not have side effects. Haskell will emphasize and verify and confirm and follow you home, sit next to you, stare at you and say, it better be pure. Java is a lot better in my opinion for that reason, because Java assumes that lambdas are pure. What happens when a language assumes things? When you and Java disagree, you know who wins. So this is one of the reasons why if you program in Haskell, you'll go home on time and your kids ask you, how was day at work, mom? And you're going to say, nah, it was boring. Everything I wrote worked. There's no fun. On the other hand, you are writing code in Java and maybe you forgot that these lambdas are pure. You go home late after a very tiring day at work and you go home and the kids ask you, how was work? How was the day? And you say, let me tell you all about it. We had a monster we had to tackle and there are stories to tell. That's one of the reasons why I love these kinds of languages. Okay, I'm a little bit being kiddish here, but the point really though is don't forget, Java may not really warn you, may not give you an error if you make mutations in lambdas because Java assumes lambdas are pure. The purity gives us laziness we talked about. So streams are inherently lazy. So what is the benefit of that approach? Let's talk about this now as different in Java versus language like Ruby. So in the case of Java, a collection of functions are applied on each element as necessary. So instead of a function being applied on the entire collection. So let's revisit this one more time. In the case of Ruby, a function was applied on the entire collection. Not so in Java. A collection of functions are applied on each element as necessary. So what Java does is it takes these functions. These are called intermediate operations. So intermediate operations, and these of course are called terminal operations. So in the case of Java, it'll take all the intermediate operations and what does it do? Are fused together. So it is going to take all these intermediate operations and it's going to fuse them together into one collection of functions. It then applies the collection of functions on each element, but only as necessary. So to understand this a little bit better, let's take a look at a slightly different example here and work with it. So rather than asking for all the people who are younger than 18 and their name in uppercase, let's say we want only the first one. So we'll go back here and we will simply say dot find first. And what if we don't have a value? What are we going to do? We'll say or else we'll say no one found. So when I run this little code now, you can see that it produced Jack as the result. Of course, in this case, we can go back and remove this operation right here. That's the imperative style. And we will simply use the functional style code right here. And it said Jack. Well, it found the first value in this collection in this output. Let's go back and remove the commented out code, run this. How does this code really work? Well, imagine you are at work and on January the 15th, the boss calls you and says, I got good news for you. You got a project, you're going to start on it, and it's due on April the 15th. Do you come out of the boss's office on January the 15th and start on it right away? Of course not. You will start on it promptly on April the 14th, isn't it? Because it's due on the 15th. That's called efficiency. Well, the point really is we don't do things until those become relevant and imminent. In fact, if you know you're going to quit on March 1st, why would you even start on this any sooner than that? The point really is by not doing things you don't have to do right now, you're able to focus on things that have to be done right now. And if things are not relevant, eventually you don't have to do it. And that's called efficiency. So find somebody who's really, really busy and give them work and they get done. But how? Because they prioritize and they don't waste time doing things that are unnecessary. That's exactly the point, is that you want to be efficient in what you do, not just simply faster. So both in life and in programming, laziness is the ultimate sophistication, as we can see here. Let's prove that right now. So when we run the code, you see you got Jack, but let's go to the person class real quick. In the person class, remember we are asking for the age first and then the name. So let's go to the age function and we will output right here, get age called for, and in this case, we will output the name of the person. Likewise, we will go ahead and say, in this case, the name itself will say get name called for. So this will be get name for, and then of course, we'll print out the details of that. But if this were eager, remember what happened in language like Ruby? It was eager and executed the first method for every single thing. If Java was eager, it will ask for the age of every single person, including this Jack and this Jill. However, in this particular case, because Jack is the result we are looking for, it will never have to touch this Jack and this Jill. May not be such a big deal in this case, but what if this were a million elements? A lot of elements after this one. We don't want to evaluate them once we find a result. So in this case, the get age is going to be called on what? It'll be called on Sarah, Bob, Paula, Paul, and Jack. However, there's one big difference though. It's not going to call the get age on all the elements first. Again, if you go back to this example and run this, notice it evaluated EaseGT50 for all the elements. Only after that, it started evaluating the double function. Not so in Java. It evaluates the group of these functions as necessary on one element at a time. So when I run this code, notice it called get age on Sarah, Bob, Paula, Paul, Jack, but then it called get name on Jack, but it never touched the second Jack and the Jill. Doesn't quite illustrate what I wanted to show here yet, isn't it? Let's try a little different example. Let's say I want the first person who is older than 20, but who is also a female. Older than 20? Well, that's Sarah, but also a female, that's Sarah too. Let's make it older than 30. That'll be this Paula. Great. So let's evaluate that. So get age is greater than 30. And then I want to say that filter, in this case, of course, and we want to say given a person, we'll say person dot get gender, and in this case, of course, is equal to gender dot female. When I run this little code, let's go ahead and comment these out for just a second. We'll come back to this and we will go ahead and put the print statement, the gender as well, so we can look at it too here. So here is the get gender. So we'll say get gender called for. So, and then of course, the name. Let's go ahead and run this little example. That's Paula. If this were eager, it would have asked for age of everyone. Gender for everyone older than 30. Name of everyone older than 30 and female. Convert all the names. only to throw away most of the work. But not so in this example. If I go back and uncomment these print statements though, what you notice right here is that when we run this, look at the sequence of the output. It called get age on Sarah. It called get age on the second Sarah. It called on Bob and Paula, then gender on Paula, name on Paula, and done. If I were to flip this over, asking for all the females first and then the age, then you notice it asks for gender on Sarah and age on Sarah right away. Gender and age on the second Sarah right away. Gender on Bob and Paula, age on Paula, and name on Paula. Look at only the first 4 lines for me. Notice get gender, get age, then again get gender and get age, then again get gender. In other words, unlike Ruby where all of the methods of one line were executed eagerly, this is being absolutely lazy. It evaluates a little bit of the first function and the second and goes as long as it can go. In other words, it fuses these functions, collection of function, apply on one element, Sarah, and if necessary on the second and the third. But the minute it finds the answer, it no longer applies it. In fact, let's go to the next level to see how laziness really plays a role in here. If we were to go back to this example, and let's remove the print line for a second, and in this case, I'm going to go ahead and say done right here. When I execute the code, you can see all that output and the done. However, if I were to go back and comment out just the last 2 lines over here, then we're not calling the terminal method. We have this collection of this terminal functions fused together, but we never call the terminal method. It's a terminal method that triggers the evaluation. As you can see in here, the result is simply done. It doesn't really execute all the intermediate functions. It's absolutely lazy. I've been working on a project where we are dealing with literally millions and millions of pieces of data. We've been running it through the functional pipeline, through lambdas. In fact, a lot of lambdas. And we're not seeing any performance degradation due to lambdas or due to pipeline. In fact, there is a benefit we get right off the bat. Not only can we have efficiency through lazy evaluation, we can also parallelize this code also more easily to get the result faster if we have a lot of data to process. So in other words, the functional style of programming is very charming. The function pipelining is beautiful. It removes the accidental complexity from the code. Compared to an imperative style code, a functional style code is a single pass through. The code begins to read like the problem statement. We can relate to what the code is doing and we can quickly understand it. It removes that accidental complexity and makes the code easier to understand. The code is cohesive. Every single line of code does one thing only. This line checks if a person is a female or male. This checks if the age is greater than 30. This gets the name. This transforms the name to uppercase. Compare this to the previous code we wrote where a line was doing multiple things, lack of cohesion. This one is easier to remove some pieces or to add some pieces. It's cohesive. A cohesive code is easier to modify. The code removes the impedance mismatch of trying to figure out and extract the details of business logic from the code. The code becomes the business logic. The code becomes easier to understand and see what it's doing. But of course, we cannot claim all this beauty is great, but we can't give performance. So to me, what really grabbed my attention in Java was not the fact that Java has lambda expressions. I've used lambdas in other languages, Ruby, Groovy, Python, to name a few, and Scala, of course, and Clojure and so on. However, all these beautiful function pipelining and expressive code is things we can only frame and celebrate, but can't really use on big projects and big data projects if the language does not support lazy evaluation. So the fact that Java supports laziness is one of the most charming features. Streams are really powerful, but there are limitations to stream as well in Java. Java streams unfortunately don't handle exceptions really well. And if you really want to do powerful streaming, there are other things you can do. For example, the reactive programming model, observables, and flow. Those ideas are not very different from streams, just that the streams implemented in Java has a few limitations. We do use streams quite extensively when we don't really have to worry about those limitations. Depends on the case. But just like I said, languages are created different. One of the reasons I got really excited about Java was not the fact that Java has lambdas. What really got me hooked on to Java was that streams are lazy. In fact, it's the laziness that drew me into Java 8, and I've been singing its praise ever since. If Java had not implemented laziness into Streams API, we wouldn't be talking about and getting excited about Java 8. And so I'll conclude by saying laziness is the ultimate sophistication, both in programming and in life. Hope that was useful. Thank you.